I'd like to talk a bit about validation and evaluation when you have a system that you think is working and you want to test if really it's appropriate or not. As objectives for the lecture, it will be to try to understand how to perform proper cross validation when you are in a deep learning setting, try to understand the different modes of validation that we have, how we adapt them to the situations that we encounter, how to make sure that we answer the proper question when we want to assess validity and performance. We'll try to learn as well how to choose the relevant measures that can be used for evaluation according to the task at hand or to the medical question or clinical question that we have. Also think about how we compare different methods together, how we compare the results, how we combine different metrics, and what are the different biases and the different things that we need to think about when we want to assess performance. In terms of outline, we will start by looking a bit in the need for validation, the questions of experimental design, the idea of ground truth or gold standard, the idea of using surrogates instead of direct measure, and so on. Then we look in different evaluation measures, looking at solutions that have been found to address performance issue with different applications. So in your application, you saw, for instance, regression, classification, and segmentation, and we focus mostly on those three. Then we'll move on to understanding central tendency or variability and comparing methods based on that. And we will try to then look about the bias that we have and what we always need to be careful about and how to better look into the errors or failure cases. Let's think a bit about the motivations that we have to try to validate or evaluate our model. Now, each time we are trying to compare to something, or especially when it's a question of classification, regression, or segmentation, you need to have something to compare to. You need to have a reference. And that's actually extremely difficult in the field of medical imaging because having a gold standard is actually very critical, and it's very, very difficult to get a good one. It's actually kind of impossible because people who use it usually do errors and they make common errors, and that's why you rarely have ground truths, you mostly have gold standards. Because everything that is related to a human decision or a human classification is potentially susceptible to be affected by error and so by noise. So let's think a bit of the type of errors that you can get. And what are the errors that are important? So you may think in terms of error, segmentation error. For instance, you say that something is lesion where it's normal, or something is not tumor when it's tumor, or you classified someone as having Alzheimer's disease whereas they were actually healthy, or the opposite. And to be able to understand what's really important when you assess your errors, you really need to understand what is a clinical need, what is a question behind the task that you have to solve. And even more than that, you have to understand why you were given a specific task. Why are we trying to do that? Why would that be useful? And if it's not useful, is there another way to go around the same problem and to better answer the background need or the root need? So as I was saying before, you need to understand what are the baseline performance, because a number in itself is completely meaningless. I was giving the example of the DICE score for TIV or for lesion. You need also to compare to other standards. What have the others done? What is currently there? Is there something that proposes a solution for the problem you are trying to solve? So you need to have a very good understanding of what's out there, so of the literature around it, and of what is expected or what is tolerable in terms of error or in terms of of failure. Another thing that is often done, especially in the context of deep learning, where you have multiple blocks and pieces, Legos, that can be matched together, used together, improved together, you need to understand what is driving the improvement in performance, or are all of the changes that you have made to your model compared to another one significantly important or important in the same way. And that's what we call ablation studies or multi-condition testing, basically where you are trying to see what is the effect of each component independently. So you change one, you keep all the others, and you look. For instance, an example for that is you change something in your architecture, but you also change your loss function. You want to see if it's actually the loss functions that made things change, the architecture, or both of them together. Similarly, when you have multiple hyperparameters and you want to tune them, you need also to think on what's the best solution, the less biased one, to properly set your hyperparameters. And we'll look into cross-validation later on this course, but you need to think of ways to assess and to best choose what's the best practice to choose your hyperparameters. Potentially, you can also get an idea with priors over it so as to better refine the areas in which you will try to choose them. In terms of the type of validation now that we can do, thing that is actually quite important to remember is that when you have, especially in medical imaging, you have usually very limited amount of data. And so there are often ways to artificially increase that number by creating synthetic data. The interesting thing when you do synthetic validation, so using only synthetic data, is that you have a perfect control over the distribution. So you actually know exactly what you are trying on, and you actually can get ground truth. While each time you have real world data and you are asking someone to label something, it means that it's only a gold standard that you get. At least with synthetic data, it can be ground truth, and you can just have a specific validation, have a very trustworthy validation, because there is no noise in the labels that you are giving. So it's usually very good as a proof of concept, because then you can really assess as if it was in vitro testing what's happening. You can follow every single parameter. However, you need to be careful because there is potentially a risk for bias if you haven't taken into account every single possible explanation, or that you are still missing samples, or that it doesn't correspond to really what you would see in real world. And that's usually why in validation you begin by validation in synthetic condition before moving on to real world data. The importance of real world data is obviously that it's representative of the truth, and it's needed to assess the generalizability. But obviously, as I was saying before, you have noisy ground truth, and usually you have limited amount of data. But it's only if you manage to make your system work to some degree in the real world that you can potentially use it and deploy it afterwards. A last way of doing validation, this time is not based on metric of evaluation that depend on a reference or depend on a ground truth that may be difficult to get, is to use surrogate validation. Because it's in medical imaging and in medical practice, what's important in the end is the clinical application. And you may find an extremely good way of segmenting lesion, increasing the dice by 0.1 maybe. So you are very proud of yourself, but maybe clinically it has absolutely no significance because it won't change the signal or the associations that you see, for instance, between age and lesion volume. However, if you think about it, maybe modifying the way you look at lesions longitudinally by removing a bit of the noise may significantly help in distinguishing between groups. So basically, surrogate validation and surrogate clinical validation, it's about comparing the strengths of association with non-associated covariates that can be through effect size, estimation of sample size, and so on. You can also, as surrogate, look into the evaluation of the cost and the impact on health economics if you were to use your method compared to another one. Finally, in some cases, one of the best way to go on is to use qualitative evaluations, or you use blind testing, such as Turing tests, where you ask your end users to compare blindly the solutions that you propose to solutions that have been proposed either by another method that is accepted commonly or by manually performed tasks. So that's about the different types of validation, the different ways you can build your validation, and we'll now dive a bit more into the different subtypes of evaluation that we get. We'll start with the image-wide type of evaluation with regular classification, where you have different ways of evaluating things and different things that you may want to evaluate. So you may think of empirical testing, empirical evaluation, either with respect to the reference or with respect to the output itself. If we think about the reference, it can be because you have a gold standard or a ground truth, and you need to look at the similarity or at the error. When you look into the output, it's more a question of the consistency, the overall appearance, the reproducibility when you have a test-retest situation. And finally, you have a completely other type of evaluation, which are the analytical evaluations. They're more with respect to the performance of the system as a whole, not with respect to the solution that is given. But it's more a question of time, the memory that is used, and the reproducibility on the same subject. Especially if you have, for instance, a dropout or system like this, where you may not have the same answer if you have any degrees of randomness. And then each time you may want to compare to others by either average rating or ranking. But we'll look into that in the last part of the course. So if you move now onto the evaluations that are voxel-wise, such as in the situation of synthesis or segmentation, and you have exactly the same type of evaluation, of type of evaluation that you may want to do, then you may want to look at different aggregation of your samples, because actually you have a different classification for each and every single voxel of your image. So you may want to look at central tendency on dispersion across samples, and again try to aggregate all the ones that you get over your samples and compare to others. So now that we have seen broadly the type of evaluation that you may want to get, we'll dive a bit more into the different specific evaluation methods that we have when we have ground truth or reference images. And we'll begin with regression. Can be either image-wide or voxel-wide. So first one is the mean absolute error. So as the name indicates, you take the absolute difference between the predicted value and the ground truth and the reference, and you take the average of that. So each time, as notation, I take y hat as a prediction and y as a ground truth. So the mean square error is basically, instead of taking the absolute value, you take the square of it and you average that. Then you have solutions or methods that actually consider the percentage of error, meaning that because the previous one, they don't change in terms of errors if the targeted value is small or large, whereas actually maybe making an error of 0.1 when you are looking at a value of 200 is not that bad compared to when you are looking at a targeted value of 0.5. So you need to take that into account, and so that's what the mean absolute percentage error is doing. In comparison, mean percentage error is just, again, percentage of error, but dropping the absolute value. The problem is that on all of those, there are some specific things that happen. That the mean square error, for instance, is very sensitive to outliers. So if you have very large difference, then suddenly it will massively increase how the value, what the cost is, basically. If you have the mean percentage error, then you may still get a 0 even if you have large errors, because it will be compensated, because you may have a very positive one and a very negative one, and then you sum them together and you end up with 0. I'm just taking a bit of time to talk to you through one of the image regression metrics, which is SSIM. And SSIM, basically, it's a measure of structural similarity, where you are using both the mean expected value and the variance, either the variance of your specific sample, of the covariance between samples, and you have it's a very classic method used either as a loss in regression or as a metric of quality of regression. So in terms of other similarity measures, you have classically the normalized cross correlation and the associated zero normalized cross correlation. So basically here you are taking for the normalized cross correlation, you are simply multiplying one predicted sample with the associated ground truth, and you divide all that by the standard deviation of each of the image. While for the zero normalized cross correlation, you take the average of the sum of the pixel of the difference between the predicted value and the associated mean of the image, and you multiply by, for each voxel, by the difference to the mean of the ground truth, and you divide by the product of the standard deviation for the two images. One of the aspects that is actually often used in terms of measure of similarity is the idea of entropy that you get in your image. And you're measuring, for instance, a difference of image, and you calculate the entropy over it. So that's the entropy of difference of image, and it's actually quite interesting because it's a way of understanding the amount of information that still stays in the difference image. So obviously, if everything is 0, it goes down to 0, while otherwise it may get boosted up massively. And so what you would want is to have it very close to 0. You have the normalized mutual information between a target A and a prediction B. And basically, it's the ratio between the product over the entropy in each image divided by the joint entropy. And it's actually one of the metrics that is often used to understand better or to improve registration methods. So now I just show you a bit in two specific examples where, for instance, we wanted to predict the age based on images, and where I calculated for each of those cases different type of prediction, different types of errors. And we have here this prediction one, where basically I changed things by value of 2, either lower or higher. In prediction 2, I have some massive error for just the first one, and then everything is exactly the value it should be predicted as. In prediction 3, it's a bit more random what's happening. And in prediction 4, it's more about averaging things up and down with different errors. And so the associated, it's interesting to look at the associated errors that we get. So for instance, with error 1, where I have alternate between an error of 2 and -2, I get that the MP is extremely low because things compensate globally or roughly. And the MSE is at 4, the MA is at 2, all good, and you see that it's exactly the same as the one that I obtain when I have an offset of strictly of 2 all the time, as is with error 3, prediction 3. You also see the effect of outliers in the MSE for prediction 2, because actually it's due to the massive difference by 20 that I have for my first sample. In terms of entropy and difference, you see that actually for the prediction 3, for which the error is basically an offset of 2, the difference is always the same. So I have always the same value of error. So the entropy of the difference is actually 0. And so you can actually look a bit more on your own at what each of them is doing. So that was all for the talk on evaluation with respect to regression. You have obviously other methods and other ways of comparing things that I haven't mentioned here. There, for instance, a measure of similarity between the obtained distributions that you can do through, for instance, Kullback library divergence. You might want to look into it if you like. But for those, compared to the direct measure of errors, it's actually, and like all the other one on similarity, it's not. It's more a question of a global. Does it globally look like what I'm expecting or not? It's not a paired way of looking at samples. So now, let's look at different types of error in classification. So you may have seen this one a while ago, but here we have different types of errors according to the ground truth that we have. So I call it ground truth. You may want to say, oh, it's gold standard, but it's as you like. And so you have your predicted values that are 0 or 1s, binary. You ground truth 0 or 1. If both say 0, that means that you are okay, it's true negative. If both says 1, you are okay, it's true positive, and otherwise you may have different type of errors. So if you say 1 while it should be 0, you are in the situation where you say positive when it's not, so it's called a false positive. It's a type 1 error. When on the opposite you say 0 while actually the ground truth says 1, you say negative where it shouldn't be, so it's a false negative, and that's a type 2 error. And you need really to remember all those definitions for all the metrics that I will talk about afterwards, and there is quite a lot. So we'll go through them slowly to try to understand what they mean and what the point is in trying to look at these equations or these measures. So the first one, sensitivity. So sensitivity means that basically you want to get all the positives that exist, you want to find them all, and you don't want to miss any. So you want to limit the number of false negatives, the proportion of the positive cases that are detected. So among all your positive cases from the ground truth, how many are there? A problem with that is that you have obviously degenerate solutions. So you may, for instance, say, oh, you may have a fabulous sensitivity for lesion segmentation if you consider that everything in your image is lesion. Obviously, you will have a perfect sensitivity, but that's still not what you like. So you always need to compensate your sensitivity with something else. And the something else is often the specificity, which is this time the proportion of the negative cases that are correctly classified, because you want as well not to miss any negative case. And that is defined as the number of true negative divided by the number of true negative plus false positives. In terms when looking at the predictions, then you may want to look at the precision, or what we call the positive predicted value. So among all the positive, the predicted positive, which are the ones that are actually positives? So it's true positive divided by true positive plus false positives. And in turn, you have the negative predicted value. So among the predicted negatives, what is the proportions of truly negatives? But that's actually not usually very meaningful when you have highly imbalanced data, especially when you are doing small segmentations. You can define as well the false positive rate as 1 minus the specificity, and the false negative rate, which is 1 minus the recall, which basically is the proportions of false negatives among the positives. Finally, you have a last one, which is the accuracy, which is basically trying to merge the positives and negatives. And it's trying to see basically the proportions of rightly classified elements over the full range of elements. But usually those are not very meaningful when you have, again, highly imbalanced data. So especially when you are trying to segment small things, or you have a class of a diagnostic class that is much, much smaller than another. In terms of binary classification, you have ways actually of combining those. And that's, for instance, the F beta score, where you can choose beta as you like, and that allows for weighting between the precision and the recall. There is also what we call the Matthews correlation coefficient, or the Cohen's kappa. And the Cohen's kappa is basically the observed accuracy minus the accuracy that you would obtain if you had a random classifier and if you follow class imbalance. So if you can stratify and you know that you have a certain proportion of each of the classes, if you randomly choose things, what do you get? And you compare that to what you observe in terms of accuracy. So now that we have all those binary classification evaluation techniques, there are also ways actually to look at that would change according to the threshold that you would take. It's extremely useful when you have to decide on a threshold on the probabilities that you get. Because most of the time you choose a 0.5 to define on your binary. On your binary, there may be other solution. And looking at operative curve, receiving operative curve, and precision recall curve is actually quite interesting in those cases. So here it's an example of different probability of classifying for a specific diagnosis, either 0 or 1. And you take the different threshold and you calculate the associated positive predicted value, true positive rate, false positive rate. You have that the precision recall curve is basically plotting the precision as a measure of sensitivity or as a measure of recall, while the receiving operative curve is actually plotting the sensitivity on the y-axis and the false positive rate, or 1 minus the specificity, on the x-axis. And to compare different measures, you would actually calculate the area under the curve of each of them. So that's for binary multiplication or binary classification. But sometimes you have multiple labels. And so you need to know how you will choose or how you will model your different things. So usually the same evaluation measure exists, it's just that you may have. And if you think of other multi-label classification measures, you have, for instance, what we call the Hamming distance. So it's basically the fractions of erroneous labels over the total number of possible labels. So for instance, imagine you have 10 classes, 10 possible classes. You will calculate it as 1 over the total number of samples times the number of labels that you would put, and you count the number of times that you didn't get the right one. Another one that you have is what we call the subset accuracy, or the exact match ratio, and it's especially useful when you have not only one label for each samples, but you have to give multiple labels, and so you are comparing the vectors that you obtain, and you're actually calculating the ratio of those for which all elements in a vector of labels that you had to give for one sample are perfectly right. The problem is that obviously it's a very strict metric, and it doesn't account for the fact that you may only have one error among the different labels you had to give for a specific sample. We'll slowly move on to the type of segmentation metric and the type of measures that you could potentially look into, and the desirable measures of accuracy, performance, overlap that you may derive from segmentation. Because each time you need to think of what is the type of error that I have. Is an error more dramatic than another, worse than another? And when you have spatial relationship, you have much more question to ask about in terms of the performance. Because for instance, it could be a question of the localization of the error. It could be a question of the distance of the error, of the relationship to the underlying signal, and so on. We'll try to look into that slowly. So let's look first into overlap type of methods. So you have the Jaccard coefficient, the dissimilarity coefficient, and the Tanimoto coefficient. So basically, the Jaccard coefficient is just the ratio of the intersection between the segmentation and your reference and the union of both. So you calculate it as true positive divided by true positive plus false positive plus false negatives. On the other hand, the dissimilarity coefficient, it's twice the intersection, and you divide by the total number observed in the segmentation and in the reference. So it's twice the true positive divided by twice the true positive plus the false positive and the false negatives. And the Tanimoto coefficient is basically a bit, so you are counting both the true positive and the true negative, and you are counting twice for zeros. The problem is that each time you include true negatives, such as with the Tanimoto coefficient, if the reference has very small number of elements, you may have a very large amount of true negatives, and that may cover a bit the signal. You also need to be careful that with those situations you have some flooring effects, and you have, because if you have many false positives and no true positives, for instance, it will always be zero. It won't cost you more to make more false detection. So you need to account for that flooring effect. And for the fact that when one of the volumes is empty, when the segmentation is empty, you may have problems of definition. You have always, as before for the binary classification, you can define accuracy and false positive rates in the same way. It's just that the number total of samples may be larger, but that's it. So that's for all type of overlap system. And you have all the binary classification type things that we discussed earlier. Some ways of looking into things, and it goes slightly towards the idea of surrogate validation, that you may actually, so you still have references, but you then don't care that much about the overlap, but more about the general volumes that you get. Because when you think about it, for instance, when you think about segmentation of gray matter, the biomarker that is then used is the volume of gray matter, not the specific location of each voxels of gray matter. And so there are ways of looking at volume similarity, or to look at the volume difference ratio. The problem is that actually it's usually dependent on the range, and you may have some definition issues when one or both of the sets are void. But it's quite interesting because sometimes it's typically the type of things that are important with respect to how you use those segmentation in the end. So since they don't reflect overlap, they cannot be used alone. So it's a first sign that actually one metric is never enough. Another sign we showed that before with the sensitivity and the specificity. Here again with the volume, because it doesn't show overlap, so it cannot be used as a proper assessment of segmentation. But it can be used in statistical assessment afterwards. Something else that people are doing actually with volumes is when you have multiple samples, and you know what is the expected sample of the ground truth, and you have your different prediction, you can actually perform a correlation assessment using, for instance, the Pearson coefficient to try to see if when you are supposed to have small volumes as per your ground truth, you also have small volumes in the method that you are using, and that it roughly follows the same type of association. That big volume for big volume in ground truth, small volume for small volume in ground truth. You can also look into that afterwards, go and see if you have any bias with respect to the volumes that you are detecting, and you can do that using Blunt-Tangman plots. But for now, we'll still focus on what you can get in terms of the validation. And we look in other measures, measuring distance. So, because you can think of it as actually it shouldn't cost the same to make a mistake at similar error, like similar distance, like what we have here on the left, top left, than making mistake with exactly the same number of errors, but really far away. And so you have different ways to do that. You have for instance, the Yasnov discrepancy measure that is measuring as a proportion of the volume the sum of the distances of errors, and the figure of merit, which is basically based on the edges that you find. So you figure out what are the borders of your segmentation, the actual one and the estimated one. And then you try to find the distance between your expected, well, the distance between your prediction and the real age. And the smaller it is, the better. Because the higher it is, the better. Finally, there is one that is used very classically, which is the Hausdorff distance. Basically, you are trying to figure out where to cost more the distance from the maximum distance between your segmentation and your reference. So that's for the validations or evaluation with respect to distance, trying to cost more when errors are made far away from where it should go. We have some segmentation evaluations that are actually related to intensity, basically saying, oh, actually making an error where the contrast that we can observe is not very strong should be less penalized than errors in locations where actually the contrast was very strong and we shouldn't have done it. So that's based on the Mahalanobis distance between the expected intensities of the segmented area and the samples that are erroneously classified. So you do that as a Jaccard coefficient for intensity, for instance, where you take your true positive and you divide by your true positive plus the sum over the errors of your the ratio of Mahalanobis distance between your error and the overall error, and the error and the reference. The thing is that this type of method is a bit biased because a lower score is not always justified, and you can actually boost a lot the histogram-based methods that are based on intensity and that will actually make more of those errors in the area of of small difference of intensity compared to the ground truth, compared to other methods that may be based on shape and so on. You also to remember that sometimes you get artifacts in your image and that actually the Mahalanobis distance that you are calculating as measure of outlierness with respect to either the reference or the segmentation is actually quite biased by that. On the catalog of evaluation methods for segmentation, you need to think also that sometimes you want to detect multiple objects. You remember what we discussed on object detection before, but when you do segmentation, you still may want to have level of granularity. You need to find when components are connected, when they are disconnected. So here you see that, for instance, you may make only on the example on the right, you may make only one error, but actually it's the one that will join the two samples that actually shouldn't, which is massively different from making all these errors here on the right examples, where you should have split the two parts of the square. And so on in the green and red boxes, there are two examples of, again, similar amount of mistakes, but one is actually cutting the areas that were supposed to be segmented in 3 different parts, while the other one is still keeping a single connected component for all of them. And so we have ways of evaluating the granularity is by using the connectivity coefficients, where basically you are taking the minimum of connected components for the segmentation and reference, and you divide by the sum of the ones that you observe for both. So for instance, on the one on the left-hand side, you have a connectivity coefficient of 1, because you have one component in the segmentation, you have one component in the reference, so the minimum of both is still 1, and you divide by the sum of them, which is 2, multiplying by 2, so it's still 1. On the right-hand side, you have normally 1 coefficient in the reference, you have 3 in the segmentation, the minimum of them is 1, and the sum of the 2 is 4. So you end up with a cognitive coefficient of 0.5. So this type of method is actually a boost for all those that use special neighborhood methods. The thing also is that, as with the volume, you can have a very, very high score, but still have absolutely no overlap between your segmentation. So it shouldn't be used in isolation either. Second small issue there is that you have no information on the size of the component. And that is sometimes useful, especially when you have very, very small components that are not detected. The other thing that is actually quite important is to, when you do that, is actually to calculate the true positive rate or false positive rate at the component basis. And this is the last one on the distance again, where you are again looking at the boundary and the boundary Jacquard here by calculating the ratio between the number of samples that belong to the joint edges divided by the union of the borders. You can also look at the average distance by calculating the minimum distance between the segmentation and the reference for both on the looking in the perspective of the reference or looking in the perspective of the segmentation, and you divide that by the sum of the borders for each. So you have looked a bit in your loss function at the dice. We have mentioned it a lot. It's one of the most classical measures of overlap that is used, and it's actually very not flawed, but you need to be very careful about how to use it and what it means. So the first thing that I wanted to show you is that actually it's very, very different when you use a dice in your evaluation to over-segment or to under-segment. And the thing is that, for instance, imagine you do the same type of error. Either you're over-segmented by one voxel around, or you are under-segmenting by one voxel. So that's what the segmin and segmax are. Or other type of error, you are just translating by one the error that you are making. And now what happens? What happens in terms of the individual connected components? It massively depends on their size. Imagine you have a cubic shape, simpler one to model, and the volume changes, and we do this segmin segmax comparison, and you see that actually for the ones that are very small, the difference is massive, and the under segmentation will always get smaller dices. When you look also at the shape of the object you are trying to segment, this will also massively impact the way your dice will evolve. Here it's looking at cubic versus spheric shapes. So you can think of that and then think that, okay, each time I'm looking at lesions, for instance, that can have a massive variation in terms of their sizes, actually having a dice of 0.2 or 0.3 for very, very small volumes is actually pretty good. So you again have to remember about what it means and what you may expect and how those things evolve. And so here in the table is basically the associated dice with respect to the cubic or spheric shape. You need to remember that the dice score is dependent on the surface area volume ratio, is dependent on the global reference, that under segmentation is massively penalized compared to over segmentation. And so what is really important is actually when you're trying to evaluate things is to really understand where the errors come from. And so there are actually methods to do that, to try to dig a bit more into where the error is and what's happening. And that tend to limit a bit the influence of the global volume. And that's what we call outline error and detection error. So outline error means everything that where, for instance, I have the right global location for a single component of element, connected component of element. So at least one, there is one voxel of overlap between the reference and the segmentation for a given connected component. But there are errors for each, and that's the outline error. On the other hand, detection error is basically when you detect a full connected component that actually doesn't exist in the contours, or inversely, there is a full connected component in the contours that is not detected in the segmentation. And so here's a paper that is actually proposing these metrics. And then you have these ways of actually calculating and defining outline error rates that range between 1 and 0, and the detection error, which is basically counting for all the elements that appear either only on the contours or only in the segmentation, the number of total elements. So then you may further refine that by saying, oh, actually, I want to separate between false positive and false negative. You know that it may depend on how you define things that are connected, because you can change this connectivity based on the neighborhood that you are choosing. If you choose a mauve neighborhood or a fun neighborhood, you cannot use them independently. And there is still some dependence on the size in the outline error. So that's a bit to cover all the segmentation types of evaluation. And now we can look into cases and other evaluation metrics. So for instance, with ordinal data, where you can base actually your evaluation on the distance between the categories, where you have hierarchical classification, where you have a tree structure, and again, you can build paths of how one solution change compared to the other. And so you use the path of distance to associate a cost for spending sometimes on a specific edge on a specific path that leads you to the other erroneous classifications that you made. And then we saw in the object detection lecture the need to look at the size of the objects to calculate the different thresholds of intersection over union, and to look at the performance for small object, large object, medium objects. And just to remind you that actually it's something that people often do also when they look into segmentation, where they will calculate their overall performance for specific subtypes of volume, so either very small volume, medium volume, or large volume. So now that we have seen a bit what can be used in terms of measures of evaluations in different situations, classification, regression, segmentation, and then cases of ordinal, hierarchical, or detection systems, is a question of how you present them. How do you report them? So you need to find a way of presenting not only the central tendency of your performance, but also the variation. And it may be useful sometimes to actually visualize them. So in terms of central tendency, it depends on the level of how symmetric your evaluation is. So you can measure that with the skewness to understand whether you can actually report the mean, or it would be better to report the median. So you report the mean only if it's a symmetric distribution, and you report the median otherwise. Usually the skewness, as a rule of thumb, if your skewness is between -1 and 1, you say that it's roughly symmetric, and beyond that, it's not, and you should favor the median as a way of presenting your data. Central tendency obviously is not enough. You need to be able to show what's the range of your performance, because you may have mean of 75 in terms of dice score, and all of your value being clustered between 73 and 76 or 77. But you may also be in a situation where actually the span of performance is much wider, where you have some cases of very, very low performance, and that you need to be able to present it. So variation, you can present it as with the standard deviation or the interquartile range, so the first quartile to the third quartile, or simply the range min max. And what can help with that is also visualizing, either with box plots, but also with violin plots, where you can better see the distribution. It's actually quite interesting when you think that you have a bimodal distribution, for instance. Ultimately, you can also do scatter plots or dot plots. So now in terms of trying to properly get what the central tendency is, trying to really assess the mean performance of your system, you actually may need what we call resampling strategies. Resampling strategies to be able to have an idea of the validation, where you want to be able to assess the performance over all samples, and you would like actually to at some point have a test set that cover at least all of the samples once. So the idea of the cross-validation, and you have used it in many other situations, and we use that a lot in the course on machine learning for biomedical application. Basically, you split your data in k folds, k subsets. You train on k minus 1 of the subset, and you test on the one that is out. And then you loop through everything to all the folds, so that every single image that is available is tested once, using obviously another training set. What you can do, if you want to be even have a better idea of the influence of the training set that you choose, is to do this k-fold separation multiple times, meaning that you will have multiple ways of splitting in k groups your initial total samples, and then you can average the results overall, one sample your results, to observe a bit the distribution and the variability in your errors. So in the limit of the k-folds, you have the leave one out, so mainly when you take as many folds as the number of samples. But that means that you can only do it k times. And you have, there is only one way of doing it, sorry. And you have a much larger variability in the results, because you train on very large data, but the one on which you test may be completely out of distribution, and so you may get very erroneous results there. On the other end of the spectrum, you have the two-fold cross-validation, which is mainly when you split half-half and training testing, and you end up with a strong limit in performance because you are massively limiting the size of the training set. So usually what happens is that for very large samples, 3 or 5 folds are chosen, and you are going towards leave one out when you have very small samples. That's practically what is done. You need to remember as well that if your classes are imbalanced, you will need to, and you know the expected proportion, you need to stratify your classes, because otherwise your results will be completely inconsistent. You need to be able to have relatively similar way of splitting the different classes or splitting the different groups across the different subsets. So that now that's the generic cross-validation as you know it from previous application. In the case of deep learning, we have a slight issue is that sometimes we split not only into train and test, but we split into train, test, and validation. And so we need to take that into account when we try to do a cross-validation. And that we can do with nested cross-validation when we have validation and test sets. So there is what we call the k times L fold cross-validation and the k times k minus 1 cross-validation. So in the k times L, which is basically the generic case, one of the generic case, you have your data split in k parts equals. You take one as a test set. So you have k minus 1 that remain. And k minus 1, you now split them in L. So that means that your validation set may be of a different size than your test set. And you train on the L minus 1, keeping 1 for the validation. And you have two internal loops to go through. The loop that will go through every single L set to choose as validation set. And the loop until each one of the k set has been used as test. And again, in the optimal scenario, you would do this split multiple times to see overall what's happening. And each time you would have to average your results. On the other hand, the k times k minus 1 cross-validation is basically you split the data in k parts and you'd keep one as test, and over the k minus 1 ones that remain, you keep one as validation and you use the k minus 2 as training set. So that means that in that case, the validation and the train and the test set are exactly the same size. And you loop until first all the k minus 1 part have been used as validation, and you can average your result there. And then you loop until all k parts have been used as tested. Now I will look a bit into testing, actually methods on permutation test and exact test. So we may have our t-statistics and approximation, but we actually can estimate the exact probability for a certain null hypothesis to occur. And that we can do it by permuting the labels and calculating exactly all the different possibilities of permutation, the probability of some events to occur. So this is based on the hypothesis of exchangeability, which means that changing the labeling would lead to similarly acceptable distributions. So an example is when you compare two methods for a given metric. So you have the null hypothesis that the methods are equivalent, and the alternate hypothesis, for instance, that method A is better than method B for a given metric. So your original labeling, you have it for method A and method B. You can calculate, for instance, the mean of results for method A and the mean for method B. And then what you do is that you pull together all the samples and you reassign label A and label B randomly. And you calculate again the mean of A and the mean of B and the number of times that, according to this fake labeling of A and B, you have A that is more than B. So then you will calculate the number of times that actually the mean difference that you observed was larger than the one that you observed with the real labeling. And you divide it by the number of permutations that you performed to get the exact probability of differing. And that's your exact test. But that's only done when you have, that is only exact when you have gone through all possible permutation. which obviously may be extremely computationally costly. So that's for the permutation test that I wanted to mention. So now that we have seen which you have these two procedures. So the t-test procedure, where your test statistic follows the t-distribution. You compare the t-statistics that you obtain that is calculated as the difference between the mean divided by the pool standard deviation multiplied by the square root of 2 over the number of samples. And you compare it to critical values to see if you can accept or reject the null hypothesis. So if your t-statistic is larger than the expected critical value for the number of degree of freedoms that you have in the t-statistics, then you have to reject the null hypothesis, meaning that there is significant difference between your methods. If it's lower, then you cannot reject the null hypothesis and you cannot say that your two populations have a different mean. With the Wilcoxon-Simon text procedure, for all the pairs, you calculate the difference. You remove all the pairs for which the difference is 0. Then you rank the magnitude of the difference and you calculate your test statistic W as the sum of the ranks multiplied by the sign of the difference. And if you have a large number of pairs, actually this W follows a normal distribution centered in 0. With the variance that is given below. And so you calculate now the probability to see according to that specific distribution that mean difference. You may want also to compare the methods and the dispersion. So for that, you have the Levin test, for instance. That is the parametric version. And you have the Brown-Forsyth test, that is the non-parametric version. We have k different groups. We call ni the number of cases in the group I, and the total number of cases, and then yij is the value measured for sample j in group I. And we then calculate different z statistics, either mean for a specific group or mean over all of them. And the difference between the parametric test and the non-parametric test is that basically z in the parametric test is defined as yij minus the mean of the y's in group I, while in the Brown-Forsyth test it's the difference with the median. And the statistics, the W statistics that you get follows an F distribution, so you can test if actually the F distribution, if the dispersion is significantly different in one case or another. Why do you think we would want to look at the dispersion? Think a bit. Think a bit and actually think of the fact that I was telling you earlier about robustness. Because basically, even if you have a slightly lower mean, you may, or a slightly lower median, you may still prefer a method where you know that you won't have massive failure cases compared to a method that it will be actually very, very good in terms of the average observation, but that will have still some catastrophic failure cases. So you need to remember that when you think about your application, when you think about your evaluation, that actually sometimes looking at dispersion is actually a good thing. Before we move on to comparing methods using multiple metrics, I wanted to go back to a slide that I skipped earlier. Ways of comparing methods and finding if the difference that we observe are indeed different or not. I just wanted to make a small comment that and I've evoked that before, is that it's not because you find a significant difference that clinically it's significant. And that's why you need additional ways of establishing that your method is indeed better or is indeed interesting. Because even if you have a significant increase in dice, it may have absolutely no incidence on the clinical outcome, on the way the biomarker or what you are producing would be used clinically. And sometimes people may prefer to be tiny bit lower in terms of dice, but being able to perform in 5 seconds instead of 8 hours. So you need to think of all that, and everything goes together basically. And so that's why you need often to compare methods using multiple metrics. Because there is not one single metric that will cover all the characteristics or the properties that you may want to expect from your method. So first, you need to choose multiple ones. You need to make sure that you cover all the properties that you want to get. And some people have used actually methods of dimensionality reduction to try to visualize or to see which method were best. You can also visualize things, for instance, with spider plots. You can do other things like average weighting, saying, oh, actually, it's more important for me the dice than the error in distance. Or actually, I count a lot on the cognitive component, and so the LTPR and LFPR will be very important. You need also to say, well, yes, I may want to weight things, but what happens if one of my metrics is not bounded? Most of them we have seen are bounded between 0 and 1, but some are not, and some it's better to be low, and for some it's better to be high. So sometimes when it's not bounded, what people do is that they divide by the worst or the worst method or the best method according to in which direction the metric is going. But the small issue with that is that as soon as you try a new method, it needs to be included it will shift if there was a shift in the boundary min-max boundary. So those are potential solutions, but they are usually not optimal. So there are other ways of dealing with things, which is using ranks. Remember that when we were talking just before about non-parametric and parametric testing, the main difference is that basically in non-parametric testing, you are using the ranks to then get to something that is normally distributed. So there is ways actually to compare using ranks, and that actually is quite interesting because you then get rid of all the questions of, my metric is high, my metric is low, my metric is not on the right direction, my metric is not bounded, and so on. So the idea is that for each of the metric and each method, you determine how many of the other methods that you are performing against perform significantly worse. You count that. So that gives you a rank for each method of the metric, with the best method, rank 1, is the one for which the number of methods performing worse is maximum. Then you sum over the different metrics the ranks that you obtain, and the winner among all your methods is the one for which the sum of ranks is minimal. And so I wanted to show you a bit what it looks like for this, using a pairwise Wilcoxon test. So here you need to remember as well that we wanted to count the methods that were worse. So that means that it's a one-tail test. we want to see in which cases we have a specific direction in the difference of means that is obtained. So one tail. So here it's exactly what the pairwise Wilcoxon test is doing is basically calculating for an array of metrics obtained for different samples, different methods. So I have a given metric. I have the solution for the different samples, and I have the solution for the different methods. So in rows the samples, in I the methods, in the columns the methods. And what I'm doing here is calculating for each method the number of other methods that are better or worse. And I calculated the associated p-value, and I store that result in my result array. Now, based on that, I can, since I have, I know on which one I have a significantly better result or worse result. I take decide on the threshold, which is at 0.05. And I count the ones that are worse. So the one for which the method that I'm choosing is significantly lower in terms of p-value. So the final rank is basically I attribute to one the one that has the highest count of worse other methods, and that's the rank final that I get for that specific metric. And then basically do that for every single metric. That's here. And for all the possible variable, for all the possible metrics or measures of evaluation. And I perform this ranking, and then I sum everything, and I report by just averaging the ranks over the different metrics. So that's finalize what we have on bias on the comparison between multiple metrics. And to finish, I just wanted to add some discussion about the question of bias and generalizability that you need always to be extremely aware of when you are dealing with medical imaging, and especially in deep learning. And I refer you to that paper that is actually extremely interesting into understanding